In this video, we're going to be looking at work and power. This video should follow the stair lab. So I'd like you to think about this question. When you came up the stairs to class this morning, did you do work? And if you remember back to the stair lab, work is just force times distance. So whether you walked up the stairs or ran up the stairs, you are doing work, because you are exerting a force, you're overcoming gravity, and you're also climbing stairs, so you're exerting this force over a distance. So work is defined as when a force acts upon an object to cause displacement of the object. And just think about displacement as movement. So you have to move. So right now you're probably watching this video in a chair, not moving. So right now you're not doing work. So in order to do work, you must cause a displacement. And that's key right there. The formula for work, as I stated in the previous slide, is going to be force times distance. The units of work are the joule, and this is not the grocery store or what you would go to Jared or Kay Jewelers to pick out. 1 joule is equal to 1 Newton times 1 meter. So if you think about it, the units for joules are basically the units of force times the units of distance. But rather than writing out Newton meters, we have a new unit called the joule. We haven't talked about kinetic or potential energy. You should remember these from previous science classes, but just for right now, add in your notes that work is equal to the change in kinetic energy. So I've written out the formula down here. Work is equal to, remember that triangle sign, the delta symbol means change in, so work is equal to the change in kinetic energy. So work can be negative, and this occurs when you have a force that acts upon a moving object to hinder its displacement. So think about the word hinder. Hinder is kind of like resists or resisting. So think about like friction. So if you have an object that's moving this way, you have friction moving in the opposite direction, excuse me. So you've got an applied force and you have friction here. So in my example here in the video, I have a baseball player sliding into a base. He's sliding along the dirt, the infield dirt, and that dirt is providing friction. It's slowing him down. So let's take a look at this example here. So you've got a bodybuilder, and the bodybuilder is lifting a set of weights, a total of 0.5 meters. He generated a force of 125 newtons. Calculate the work done. So our work formula is W equals FD. We're going to go ahead and substitute in the 125 newtons for our force, and we're going to multiply that by the total distance that our bodybuilder is lifting the weights, which is 0.5 meters. So when we calculate this out in our calculator, we get 62.5 joules. And that is the work that is being done in this case when the weights are being lifted up. In this example, we're moving a crate. So when moving a crate, a force of 540 newtons was applied. A total of 1,080 joules of work was done. How far was the crate moved? So in this case, we're going to rearrange our work formula. So we've got our triangle here, and you should have gotten this on one of the previous slides, but we do have a triangle here. So whenever we're trying to manipulate our formula, we cover up the variable that we're solving for. In this case, it's distance, and we're just left with work over force. So work over force. So our work in this case is 1,080 joules of work, and the force is 540 newtons. And if you calculate this out, you end up with a even 2 meters of distance. So our crate was moved 2 meters. All right, in this third example, we have a 10 kilogram mass. It experiences an acceleration of 3 meters per second for 25 meters. Calculate the total work done. Okay, so let's go ahead and work this out. We have our formula, work equals force times distance. but we can't really just plug in anything here because we're given a mass, an acceleration, and a distance. Okay, so in order to get a force, we have to first go ahead and convert our mass into a force. So we've got that force of gravity. So we've got 10 kilograms, and we're going to multiply that by 9.81 meters per second squared. Okay, and that is going to give us a total of 98.1 newtons of force. So just like when we went up the stairs in the stair lab, we converted our body weight to a mass, or sorry, yes, we converted our body weight to a mass, and then we used that mass in our force calculations. So let's go ahead and plug this in. So our force is 98.1 newtons, and this is happening over 25 meters. And this ends up, when we work this out, being 2452.5 joules. And that is the total amount of work done in this case. So anytime you're working with one of these problems and you see a mass, you need to go ahead and convert that to a weight or a force of gravity. Power is the rate at which work is done. Our formula for power is work divided by time. So in the stair lab, we took our work, which we found that whether you're running or walking, you end up doing the same amount of work. But the difference comes in the power. So if I am running up the stairs, the amount of time it takes me is less. So I'm generating more power when I go up the stairs quickly than if I walk. The units of power are the watts. And if you think about that word, you've probably heard it before. So we have watts in light bulbs at home. Common wattages in light bulbs are like 60 watts, 75 watts. Sometimes in garages, you'll see like 100-watt light bulbs, and usually the more wattage, the brighter the light bulb is. You will also see kilowatts. Kilowatts are what the electric company comes out and reads your meter in. So you're billed in kilowatts. Now, most machines are built to do work on objects. All objects are typically described by a power rating, and you've heard of one of these before, and that is the horsepower. Horsepower is very commonly used in cars, and you'll see it in other machines, other motors, like golf carts, lawnmowers, any type of like yard machine, like leaf blowers. So you'll see this before. Or you've probably seen this before. So I've got a Ferrari here. This is a SF90, very expensive car. I looked this up, and the price tag of this car is about $335,000. Definitely out of my price range. So the Ferrari SF90 has 986 horsepower. That is absolutely insane. So to get the same amount of power, you would need 986 horses. Now, most horses, at least it's my understanding, that a horse is about 20 grand. I might be wrong. So it would probably cost you more in horses to get the same amount of horsepower than it would to just buy this car. So just something to consider if you're in the market for horsepower. So when we did the stair lab, we did calculate power. Now, just kind of compare your power to a horsepower. So when I did a quick poll in class, most students generated between 200 and 400 watts of power. If you didn't do the stair lab yet, your power is probably going to be in that range somewhere. Whether you're walking or running, I was just looking at the greatest power. And I asked students to compare their power to a horsepower. So compare this number to a horsepower. Most students were not able to generate a horsepower. Like I said, our highest that I saw, I think, was around 400. So what could we do to increase our power to get it up to a horsepower? Well, the answer is right here. So the faster we go, we can't really control our mass, but the faster we go, the more power we end up generating. Now you could, if you wanted to, change your work a little bit, because remember, work is force over distance. In order to generate more force, you would need more mass. So the only way to really increase your mass is to perhaps put on a backpack or have another student carry another student up the stairs, which is definitely unsafe and I don't recommend doing, but that would be one way to increase your mass and therefore increase the force, which would then increase the work, which would then increase the power. Hope I didn't lose you there. But the easiest way to increase your horsepower is simply to move faster, which I guess this is the last question. I just kind of went over this in the previous slide, but again, if you didn't generate at least 1 horsepower, what could you do differently next time? And again, that would be to increase our speed going up the stairs.